So let's talk about the way that light can look through a glass. And so I have a glass full of water here. And when I do this, first of all, you can look and see that the whiteboard behind it actually kind of shrinks because of the way that the light passes through the water differently. You can see that the box that's on the table, it also appears smaller, even though you can see the edge of the box out the left-hand side of the glass. You can see the entire box inside of the glass of water because of the way that light will bend a little bit inside of water. And so if I take a straw and I put it in there, it looks different inside the water as opposed to outside of the water. It looks a little bit larger while it's inside of the water and smaller while it's outside of the water. And so when you pass light through from one substance into the next, it changes the way that you see things. And so this is the premise of what we're going to be working on when we're talking about Snell's law. So when we talk about how the straw looks different in the water, or anything from behind looks different coming through the water, it's because of this quality called your refractive index. And your refractive index is a comparison of the speed of light in a vacuum to the speed of light in any given substance. And so the speed of light in the vacuum is as fast as you can go. Putting it in a substance, there's more particles, and so it'll always slow the light down. So when you take the speed of light in a vacuum and divide it by the speed of light in the substance, that will give you your n value. The slower that the light goes in the substance, the more times it would fit into that, and the bigger your n value. Most n values that we'll encounter are between 1 and maybe 3 or 4. If you're getting up toward 4, it's slowing down quite a bit. So the way that we see this written is n equals c over v, and we have to keep in mind that c is going to be the speed of light. It's a constant, and we will use 3 times 10 to the 8th meters per second for that. So when we're talking about an n value, the higher the n value that you have, it means that the speed of light in that substance is getting slower and slower and slower. So if you take a look at Snell's law explains a little bit mathematically of why you see something different from the air to the water, or really any one substance to another. And so what happens is, this is what Snell's law looks like. It's n1 sine theta 1 equals n2 times sine theta 2. And so if you have two different substances, let's say in this case that we have air and water, we take the n of air, and we just talked about that in a bit ago, and then times sine theta of the angle that is made with the perpendicular. So from this straight up and down dotted line, the angle that goes out from there. So you take the sine of that angle times the n1 is equal to the sine of this angle that's made inside the next substance, so in this case water, times the n of water. And so when you multiply those two and you multiply those two, they end up being the same. And so as n goes up, your theta will get tighter and tighter and tighter. And the difference between the n2, the greater the difference in the angles as well. So if I take this laser and shine it down this line that I have here, it's a little bit tough to see, but if I bring this down the line here, you can see that it bends and goes through the block. And it's not quite as straight as, the line's nice and straight, but it's at a different angle than how it comes into the block. And so I'm going to take and put a protractor on both sides, and we can measure that. So now that I have a protractor on here, I can shine my laser down that line again, and it's coming straight down the line. And you can see that that as it crosses the end there, and again, we're going from the perpendicular line here, and so we can go over 10, 20, 30, about 33 degrees is where it's coming through over there, right about here. And so up here, I've got 45 degrees. Down here, 10, from the 90, I'm going to count over 10, 20, 30. I'm right at about 33 degrees. So now that I know my measurements in here, I know that my theta 1 is 45 degrees, my theta 2 is 33 degrees, I can figure out what the n of the block is. And so n of air is always going to be about 1.00. And in actuality, it's 1.0003. But for everything that we're doing, there's no purpose in going that many decimals to get down to something that's really small. So for n of air, we'll use 1.00. And if we're looking for n of the block, that'll be our n2, and that's what we're looking for here. And so if we take and we say n1 sine theta 1 equals n2 sine theta 2, then we can solve for n2. In here we can put our numbers. We can say 1.00 sine theta 1 is 45, so sine of 45, equals n2 sine of 33. And to solve for the n2 then, we'll divide both sides by the sine of 33. And I'll show you in a moment how to stick that in your calculator. So we're left with n2 here. So the way that that'll be set up is we'll say 1.00 sine of 45 divided by the sine of 33, and that will give us a number. It will be the n for n2. And so the way that you can do this is you'll just put it in just like this. You'll say 1.00 times, and you'll go sine of 45. In this calculator, I have to put a parentheses on there. And then I would just go divided by the sine of 33, put a parentheses on that back part there. Divided by the sine of 33. It didn't do it the first time. And when I do that, I end up with 1.298. We'll just say 1.3. It will be our answer, equals n2. And n values don't have any units with them. They're just a number. So by doing that, we have 1.3 equals our n2. Let's say you also wanted to know how fast the light was traveling in the block. And so because you know that n equals c over v, you could say that n of the block, so 1.3, put too many there, 1.3 is equal to 3.0 times 10 to the 8th divided by v, and we need to solve for v. So I'll multiply both sides by v, and then I'll divide by 1.3. So I'll have 3.0 times 10 to the 8th divided by 1.3 will be equal to the speed of the light in the block. So if I take that, I stick it in my calculator, and I have 3 times 10 to the 8th, and then divided by 1.3. Here I end up with 2.3 times 10 to the 8th. It has it written out in long form here, but this ends up being 2.3 times 10 to the 8th meters per second. And so light in a vacuum is traveling at 3 times 10 to the 8th meters per second. Light, once it gets inside the block, there's more particles and more things to slow it down, and so it ends up traveling at 2.3 times 10 to the 8th meters per second. So still really, really fast, but not quite as fast as going through a vacuum. The other situation you might encounter is where you would have to solve for an angle. Let's say that you know that n1 is 1.00, and you may have theta 1 equals, I don't know, let's say 52 degrees. And we'll say that n2 is 1.25, and we want to know theta 2. Well, we still set up with what we have. n1 sine theta 1 equals n2 sine theta 2. And this time we'll have to solve for theta 2, so it'll have a couple of different steps in it. So the first thing we would do is to divide by n2 on both sides. And when we do that, we get n1 sine theta 1 divided by n2 equals sine theta 2. From there, we can put our numbers in there. We would have 1.00 times the sine of 52 divided by this n2, sorry, not sine, divided by 1.25. And that would still be sine theta 2. So to put those calculations in, you would say 1.00, you actually don't need that part, but we'll keep it in there, times the sine of 52, and then divided by 1.25. And when we do that, we end up with 0.6304 something something. So we'll say 0.630 equals the sine of theta 2. Well, that doesn't give us our final answer yet because we need to know what theta 2 by itself is. So to get that, we'll say the inverse sine, and in most calculators, it's pressing the second button or the inverse button, then the sine button. It'll show up like this, sine minus 1. And then we put our number in here, 0.630 will equal our theta 2. So we'll do that in this calculator. We'll say the inverse sine, so we'll go second sine of 0.630. And when we do that, we get that it is 39.050 something 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 degrees. And so we can just say 39 degrees equals theta 2. And so if you're not sure what you're doing in these, do it side by side with what I'm doing, because every calculator will be somewhat similar in that regard. And there's only two things that you can be solving for in these. You either have both ends and one theta and you're solving for the other theta, or you have one n and both thetas and you're solving for n2. Or n1, you're solving for one of the n's in there. Let's look at this from the perspective of the wave fronts. We know that the rays travel through like we had with the theta 1 and the theta 2. And we know that in air, the speed of the light in the air is greater than the speed of light in the glass. And so as it comes through, the frequency stays the same. So the color of the light stays the same. That indicates that the frequency stays the same. And we know that in the glass, the speed of light in that glass is lower than that in the air. And so if the speed goes down and the frequency stays the same, then the wavelength of that wave is also going down. You can see that represented by the way that the wavefront lines become tighter as that light passes into the glass. So anytime you have the light passing in, most of the time we'll be drawing just the rays and we'll be making those calculations. But if it's a question that's looking at how the wavefront travels in there, because the velocity drops in the glass, the wavelength also drops. If you were to look at it and the wavefronts, the lines for the wavefronts were to be farther apart, it would mean that it has a higher velocity than the substance that it came from. And so sometimes you may not be dealing with this in the way of the rays, but you're dealing with it conceptually in the way that the wavefront approaches the barrier between the substances and then how it looks different in the substance. And so because the frequency stays consistent, if the velocity of the wave in the new substance goes down, the wavelength also goes down, and that'll be represented by tighter lines representing the wavelengths. In the example that we looked at ahead of this, N1 was less than N2, and in many situations that's what we'll be dealing with, particularly because a lot of times we're dealing with the first substance being air. In this situation, when we're dealing with total internal reflection, the light ray is going to originate in the substance that has the higher refractive index. So the first substance where the ray is originating, our N1 is going to be greater than the N2 that it exits. And so this takes place if you have a substance and you put a laser right up against it, there'll be a point where you achieve total internal reflection. So if you look at the diagram that's shown here and you look at line 1, line 1 is exiting the substance into the air, but it's perpendicular to the surface of that substance. And so theta 1 ends up equaling 0, and so theta 2 also equals 0. But in the other ones, in 2 and in 3 and in 4, each time you can see that theta 2 ends up getting larger than theta 1 was. And so as the light exits into the air or whatever substance it is, remember that the N value where it's exiting has to be lower. And as it exits there, because that N value is lower, that angle, theta 2, ends up getting larger. Well, there comes a point where that theta 2 angle ends up being 90 degrees. And so when that ends up being 90 degrees, and you can see that represented with line 4 on there. When it ends up being 90 degrees, the light no longer escapes the substance that it's in. And so it reflects back into that substance. So let's say that's a block of glass. And at line 4, that ends up being your critical angle. And what it means is that from your critical angle or anything larger, when theta 1 is equal to that, you will always end up with total internal reflection because your theta 2 is going to be a number that is 90 degrees or greater. And so you can see in rays 4 and 5 that as that beam approaches the surface, in 4, that theta would end up being 90 degrees, and you can see that it reflects back just at the same angle that it approached the surface. And in 5, we're past that 90 degree mark, and so it too reflects back at the same angle at which it approaches the surface. So let's take a look at the calculations for critical angle. Remember that in the situation where we can achieve critical angle, our theta 1 comes with our N1 and it becomes 90 degrees. Theta 2 is 90 degrees as it heads into N2. So N1 has a larger N value than N2 does, so it causes that larger angle. And so in the data book, we have the setup for our Snell's law equations. Our N1 over N2 is equal to sine theta 2 over sine theta 1 equals V2 over V1. And so that ratio occurs throughout any of our Snell's law type of relationships. And so for what we're doing here, we're going to take off this part. We don't need that part. And we're going to focus on what's happening with N1 over N2 and sine theta 2 over sine theta 1. Well, we know in this situation that sine theta 2 is sine of 90 degrees, which gives us 1. And so we have N1 over N2 is going to be equal to 1 over sine theta 1. And so to make this a more functional equation, we're going to take the inverse of it. And so we'll take 1 over sine theta 1, taking the inverse of that will just give us sine theta 1. And then if we take the inverse of what we have here, we have N2 over N1. And so that's the basic equation that you'll see for critical angle. You may also see it, because that sine theta 1 is your critical angle, you may see it written as sine C for critical angle equals N2 over N1. And that's just making the assumption that theta 2 is at 90 degrees. You may also see it as that theta C is equal to 1 over N1, because in that situation, the assumption is being made that air is your second substance that it's leaving to. So let's look at an example here. And in this situation, we are trying to figure out what our theta 1 is based on the information we know about N1 and N2. And so in this situation, N1 is going to be equal to 1.21 and N2 is air. And so we have sine theta 1 equals N2 over N1. And so we can take and put our numbers in, 1 over 1.21. And so when we do that, sine theta C is going to be equal to what we have here. So that is 0.826. And so we'll take the inverse sine of that. And on your calculator, you can just do inverse sine of your answer. And so when you do that, you end up with an answer of 55.7 degrees. And that ends up being your critical angle in this situation. In this next situation, we know what the critical angle is, and we're going to be having it exit out to air. And so we can use the equation that the sine of our critical angle is equal to N2 over N1, and we know what those values are. And so we have, we can say that N1 is equal to N2 over the sine of our critical angle. And so in this situation, we have 1 for our N2 because it's air, and then divided by the sine of 62.0. And when we divide those out, we get our N value of 1.13. So the refractive index of that
Substance is 1.13, and it's caused by that critical angle of 62.0 degrees.